Right, so now you saw that angular acceleration denoted by alpha. When do you have angular acceleration? When your angular velocity is changing. Okay. And when did you have linear acceleration? When your linear velocity was changing. What caused linear acceleration? Forces cause linear acceleration. And what we'll show you is torques cause angular acceleration. Torques denoted by tau. Okay. That's the symbol used. Okay. So I'm going to show you. So now let's go to the simulation. Okay. So I'm going to put a 10 kg object here. Okay. And if I remove these things, what will happen? So this is, there's the fulcrum. And let's see, how do I remove? So the object rotated clockwise. Okay. Now let me reset 10 kg. Now if I put the 10 kg object here, what will happen? It'll rotate again. It'll rotate faster. Okay. You've applied the same force, but further from the fulcrum, and it'll give it a greater acceleration. Okay. So the torque depends on the force you apply and the perpendicular distance from the axis of rotation. And this is called the moment arm or the lever arm. Okay, so it depends on the force and this distance. Okay, so all right, so the torque forces can cause linear motion and rotational motion. So this force can cause rotational motion. Okay, so in this object there, the object is fixed to rotate about this axis, and this will make the object rotate counterclockwise. This force will make it rotate clockwise. Okay. The efficacy of a force in causing rotational motion depends on its moment arm. So for instance, let's say this object was nailed there. If I take this force, the same force, and I apply it at this location, what will happen? And imagine that was the only force acting on it.
Nothing.
Nothing. It won't rotate. The force is the same, and when I reduce this moment arm to 0, its torque went to 0. Okay? So the efficacy of a force in causing rotational motion depends on its moment arm. That's the moment arm. The moment arm is the perpendicular distance of the line of the force from the axis of rotation. Okay? Greater the moment arm, greater the torque. The product of force and moment arm is called the torque. Okay, so torque is the product of force and the moment arm. Okay. And so for this, for a given force, the greater the moment arm, greater the torque. Have you guys used a wrench? Okay. You use a larger wrench, and it becomes easier to solve, to unscrew the nut. For the same force, a larger wrench gives you a greater moment arm and gives you a greater torque. Okay. So that's what's happening. All right, so in this example, so now you know why. Look at the doors. The doorknob, where is it placed? On the end, as far away from the hinge as possible. Okay, now you understand why. They're giving you the maximum moment arm, okay, by placing it there. If they place the doorknob there, you would get half the torque for the same force. Okay. All right, so in this thing, so obviously there's the hinge, and this moment arm is smaller than this moment arm. So smaller than this moment arm. The same force, this is a greater torque. This is a smaller force and same moment arm, so this is a smaller torque than that. And how about this guy compared to, let's say we compare this to this guy. let's say the forces are the same, which between these two will have greater torque? A. Okay, so this force, there is the moment arm for this guy. Okay, and the moment arm is smaller than that moment arm. Okay. All right, so it turns out, so here's just like force, the torque is a vector. And for this object, if that's the axis of rotation and you apply the force at this location, the torque is given by R, a vector from the axis of rotation to the point of application, cross F, R cross F. Okay? And it turns out that the magnitude of the torque is R times F times sine phi, where phi is that angle. Okay. What is sine 0? 0. So if you apply a force in this direction, you won't be able to rotate them. If you apply the force in that direction, pointing to the axis, you won't be able to rotate it. Okay? So when is the torque maximum? When this angle is 90 degrees, when the force is perpendicular to R. Okay? All right, so keep that in mind. Okay. Now, what this page does is shows you, derive this formula. Force is mass times acceleration. That was Newton's second law. By the way, when was this true?
When?
Mm-hmm. Is that the correct form of Newton's second law? Is that the most general form of Newton's second law?
No, it's acceleration equals force divided by mass. Is acceleration
No.
correct?
What is the most general form of Newton's second law? F, very good. M equal to, force equal to dP by dt. When does this reduce to mass times acceleration? Very good, my friend. So see, this guy was d by dt of m times velocity, dm by dt plus m times dv by dt. Okay. So force, the most general form for force is dm by dt v plus m dv by dt, which is a. Okay, for most of our application, dm by dt is 0. So this term is 0 and f equal to ma. Okay. All right, so there was Newton's second law as long as the mass was constant. Okay. So similarly, we'll give you an equation for rotational motion. Torque is equal to I times alpha. Okay, so this will be the Newton's second law. When do you think it will be valid? Very good. I is constant. Okay, so we'll give you a formula where I is not constant a little later. Okay, all right. So we'll give you this formula when I is constant. Okay. All right. So here's a sort of a cooked up example. Okay, so imagine a string, a ball attached to a string, and this is rotating. Okay, what you're going to do is you're going to apply a force to the ball, and so the ball is going to accelerate. It's going to have a tangential acceleration, except that it's confined to move in a circle. So there's a tangential acceleration. The torque is this force times the moment arm. Force, the tangential force times the moment arm. This force gives you a tangential acceleration, but that tangential acceleration is related to angular acceleration. Okay, the tangential acceleration is alpha times r times alpha, okay? Okay, so we're going to substitute that. Tangential acceleration is r times alpha, and there's the other r. So you get m r square times alpha. Well, but m r square is the moment of inertia of that object about that axis. So torque is I times alpha. So here's a very cheap derivation of Newton's second law for rotational motion. Okay. Torque is I times alpha. Okay. Okay, here's what I want you to notice. Again, forces get replaced by torques in rotational motion, masses get replaced by moment of inertia, and linear acceleration got replaced by angular acceleration. Okay. So, and we had said that net force was equal to that. What does the net force mean? I'm sorry? That's right. If more than one force is acting, if several forces are acting, you just add up all the forces. Similarly, you can do net torque. If several torques are acting, you just add up the torques. Okay. So here's a situation. So let's say here is a pulley wheel. This mass is trying to rotate it clockwise. This guy is trying to rotate it counterclockwise. You just add them up. Okay. And remember, we took counterclockwise torques as positive and clockwise torques as negative. Okay, so you just add them up. So net torque is equal to I times alpha. Okay, I don't know if you notice your cars, your car specs will give you torques that the engine can provide. Okay, so the power of the car is the torque times the angular speed. That's the RPM that you see in your dials. Okay, the RPM the engine is providing. Okay, so the power is torque times omega. All right, here's here's how you derive it. Okay, so this is the infinitesimal amount of work done. This force, this object is fixed to rotate about that point, and you apply this force, and when you apply this force, the object moved a small, this point moved a small, this infinitesimal displacement there. Okay, and the work done was the component of the force in this direction, which was F sine theta, sine phi. F sine phi gives you a force, component of the force in this direction times ds. F sine phi, and ds is r d theta, Okay, but if you look at the formula for the torque, the magnitude of the torque, where r, phi, and f, and that's the magnitude of the torque. Okay, so F sine phi r, that's the torque. There's the torque d theta. Okay. And power is the rate at which you're doing work, dw by dt, tau d theta by dt, which is omega. Okay, so the rate at which this force is doing work is the torque it's applying times the angular velocity of this object. Okay. So the rate at which a motor is doing work, for instance, is the torque it applies times the RPM at which the whatever object is rotating. Okay. So this is useful if you look at the specs for cars and stuff like that. Yeah. If you have a engine that's applying high torques at high RPMs, you got a powerful beast. Yeah. Yeah. What is the most powerful beast you've handled, my friend?
480 foot-pound at 3K RPM,
Mhm.
or 500, so about 480.
Which one?
383 strokes, small block. Chevy.
Okay, so All right, so that is the power. That's the rate at which work is being done. Okay, that's it. So what? How many horsepower was that? Do you remember how many horsepower were?
Yeah, it's about 480, because it doesn't,
Mhm.
that's that high.
Okay.
So 500 foot-pound
Mhm.
times.
Okay. All right, now we're going to give you the work energy theorem for rotational motion. Let me remind you the work energy theorem for linear motion. Let's say there were several forces acting on this object, and so on. There was the initial velocity and there was the final velocity. The work energy theorem said the net work done, that is the work done by all the forces acting on the object, shows up as change in kinetic energy. Shows up as change in kinetic energy. That is the net work done by all the forces is equal to final kinetic energy minus initial kinetic energy. If the net work done is zero, your kinetic energy doesn't change. If the net work done is positive, your kinetic energy increases. When you apply brakes, net work done is negative and kinetic energy decreases. Okay? There's a similar formula for rotational motion. In rotational motion, what do work? Torques do work. Okay? And so the work done by the torques, it shows up as change in rotational kinetic energy. Okay? All right, so the net work done is change in rotational kinetic energy. So the work energy theorem states that the net work done by all the torques acting on the object is equal to the change in rotational kinetic energy of the object. Okay? All right, so here's what was going on. We started off this chapter by looking at two motions. So this was an object moving in one dimension. Okay? And then here was a rigid object rotating about this axis. Okay, a rigid object meaning a disc or a wheel or whatever rotating about this axis. And at first blush, these two guys are not even related. They're very different motion. But what we have learned is that they are indeed, the equations describing these motions are very similar. Okay? To describe this motion, you needed this guy, and to describe this motion, you needed this guy. Okay? And indeed, in fact, they are cousins. Okay? And that's what this slide shows you. Okay? So these were the equations that you studied over the first 9 chapters. And here are the corresponding equations for angular motion. Okay? So, and this was the replacement. You replace x by theta, v by omega, a by alpha, force by torques, mass by moment of inertia, linear momentum by angular momentum, P by L, and you get all the corresponding equations. Okay. All you have to remember is this recipe. So, see, linear velocity was dx by dt, angular velocity was d theta by dt. Okay. Sum of the force, which is net force, was equal to mass times acceleration. Sum of the torques, net torque is I times alpha. A is dv by dt, alpha is d omega by dt. These equations were true for when A was constant. Similarly, when alpha is constant, you get similar kinematic equations. Okay. Work done when force change with position was given by that. Similarly, we haven't shown you this, but similar equation works when work done is the torque is a function of theta. Okay. This is linear kinetic energy, rotational kinetic energy. Mass got replaced by I, V got replaced by omega. Okay. Power is tau times omega, that's the rate at which you're doing work, and power for linear motion was force times the velocity of the object. Okay. Here's angular momentum, I times omega, linear momentum is m times v. Okay. So here's the real form of Newton's second law, the most general form of Newton's second law. F is dp by dt, and similarly tau is dl by dt, which will come up to next chapter. Okay. All right, I'm just going to show you some fun stuff. And as engineers, you'll have to deal with this. Okay, so here's a CD. You guys have, do any of you guys still use a CD? All right. Have you guys ever used a CD? All right. So, the information is written on this line. Okay. And, okay, so what happens is a laser reads, so a laser is pointed like that, and it's reading it. And so the disk rotates. So as the disk rotates this way, that information is read by the laser. And all the laser has to do is move in this direction to read the CD. Now the deal is the following. Okay, for the laser to read, the line has to move at constant speed underneath the laser. All right, you just learned a minute ago, the speed, linear speed, V is r times omega. R is the distance from the axis of rotation, and omega is the angular speed. Now, if this has to be constant, what do you have to do? As r is changing, omega has to change. So you got to have a variable speed motor. Okay, to read that. Okay. Now here's the next thing. I'll show you a very neat thing. All right, so the information is packed on this line. Now, what would you have to do if you wanted to pack more information?
Make the space between loops smaller.
Exactly. Okay. Now, so here's a very important fact you'll learn. Okay, you're reading it using a laser. Okay, and laser is light, and this is the wavelength of light. Okay, so wavelength of light is denoted by lambda. Okay, if you use this light, the smallest object you can read is that object, the size of the wavelength. You can't read anything smaller. All right, so our friend just suggested he wanted to pack more information. You just make the lines closer together. Well, you make the lines closer together, you'd better have a better laser, a laser of shorter wavelength. And that's what happened. Okay, so you first had CDs, and the groove spacing was 1.6 micrometers. A micrometer is roughly the size of a cell. Then you went to DVDs. They had a laser that was using a smaller wavelength, almost half the wavelength. And you see, you could pack 5 times the information. How come 5 times? This is half the wavelength, twice. This is area, 2 square is 4. So 5 times the information. The Blu-ray was again twice as short wavelength. Okay, the wavelength was half, again roughly 5 times the information. Okay, all right. So you got laser with higher and higher frequency, smaller and smaller wavelengths, and you could pack more information. Okay, so this is roughly the best we have now, Blu-ray, or at least cheaply available. And look at this. You're packing information 1 gigabyte per kilometer. Okay, so if you unfold this line, a kilometer is from here to the Embry-Riddle campus. Okay, so on that distance, you're packing 1 gigabyte of information. And by the way, 1 gigabyte of information, for instance, when I'm recording these lectures for 1 hour of lecture, that's 1 gigabyte. Okay? I haven't gotten to the punchline yet. So that's 1 gigabyte per kilometer. Inside your cell, you have a DNA that contains 3 gigabytes of information. That is a 46 chromosome. Anyway, if you stretch out the DNA, that's 2 meters long. So that's 1.5 gigabytes per meter. The information is 1,000 times more dense. Yeah. And your body is, so that information is all folded up, and then you gotta unfold it when you have to read. Every time you make proteins and stuff like that, you gotta unfold it, read it, zip it back up, back it back up. That's an amazing thing. All right, guys. So that's it for today.